Is it visible now?
Yeah.
Hi. Hi. Good morning, everyone.
Yeah, I think we'll get started. So,
Sure. Yeah.
Yeah, Zafar, please give your brief introduction before getting started so that everyone are aware of your expertise and your strength.
Sure.
Okay.
So, hi, everyone. Good morning. So myself, Zafar, and I have total 15 years of experience in embedded system. So I started basically with microcontrollers, and it was all bare metal. And moving forward, I moved into the embedded Linux development side. And presently, I'm working in a technology company called Pure Li-Fi, which is based on Scotland. So our main focus is to develop the technology called Li-Fi, which is very soon going to replace Wi-Fi. And Li-Fi is a term which was given by Professor Harald, and basically it is technology where we have embedded the data into the light. So like now we are reaching out to all the devices over the light. The data is getting transmitted between the device and the access point using the lights. So in the future, it's going to be every tube or bulb or any lamp in your household is going to be acting as an access point. And it's going to replace the routers which you are using in your home. So instead today, speaking on the Li-Fi, I am basically, my focus is more on speaking on the platform, because from a couple of years when we started um, hiring people for multiple roles, we are seeing that the new students who is coming out, basically they talk a lot about the application, but we are losing the focus on the technology. So we today, if we go and search people who work on core embedded side, so we don't get anyone, because even the way how we do the project in academics got changed. So everyone basically do their project using Arduino or Raspberry Pi, and when they use Arduino, most of the Arduino is having its own inbuilt libraries. Uh, or when we speak on Raspberry Pi, so people are mostly using Python. So it mostly the people's focus moved on application side. So we keep on thinking of the end product, but at the same time, we keep on losing our knowledge on the technology side. So today, we don't find anyone who works on Linux kernel. And in the industry, whenever you are developing a new technology, we have basically we need expertise who should understand a very in depth actually about electronics as well as the embedded software. Either it's a Linux based or a non Linux based, RTOS based, or just an interrupt driven system. So that's why I choose the topic embedded system and Linux. The reason is because most of our products and the market requirement is actually towards the embedded Linux side. So let's get started. Mm,
Yeah, could you please go on presentable mode?
Sure.
And for other participants, request is to go on mute. And if any questions are there, you can just post it in the chat window. Later we can take it up. Let the presenter go through his presentation. Okay, thanks.
So if I define the embedded system, so basically embedded system is a processor or control based system which works with the combination of hardware and software. So any the requirement from any embedded software, any embedded engineer is to have the knowledge of software and hardware both. So only software, no. Only hardware, also no. It is required from expertise on both the side, because most of the time we keep on developing the drivers, and drivers are something which is basically driving, which is directly interacting with the hardware. So um, we keep on getting new peripherals every day, and we have to interface those peripherals with the existing hardware, or maybe we have to write some software for that for the new hardware, which is from an which may be from existing or new vendors. For example, we have a new core that's called RISC-V, and we have to keep on writing a lot of drivers for that. So there is a good knowledge required for microcontroller. I mean the hardware side, as well as I mean everything about the hardware, like what is the architecture, how many registers it's having, and what are the different peripherals it's having. So sometimes it can also be called as the network of controller processors, memory, input output peripherals. So basically, when you look the a block diagram of any embedded system, so it is having connection between different peripherals, like the SPI peripherals, the I2C peripherals, uh, and the internal memories like RAM, ROM, and different uh, register sets with the ALU. And we have three different type of embedded systems. One is the OS list. So these were like it's a it's this kind of embedded system is mostly we can find in microcontrollers, which is running in a while loop, and it is also sometime based on interrupt driven system. Basically all the real time work is done by the interrupts. So we keep on writing interrupt service routines, and whenever any interrupt occurs, so that particular task is getting done in interrupt service routine. Another one is RTOS based. So when we are getting multiple peripherals and it is getting unmanageable from our while driven code or interrupt driven code, and we have enough processing power as well as a good speed, then we use RTOS. For example, if we have 8051 based microcontroller, so 8051 basically works on close to 12 megahertz, 11.0592 megahertz. So, and it's a 8-bit microcontroller, so you don't have enough processing power so that it can handle RTOS. Because when we introduce RTOS, definitely it's having many overheads, because there is a scheduler which keeps on scheduling the different tasks. So it is recommended to be used in such system where we have enough processing power. So we can create multiple tasks, and each task can be can handle multiple peripherals. So we have many freely available RTOSs like FreeRTOS, ThreadX. ThreadX now belongs to uh, Microsoft, and its name has been changed to even FreeRTOS belongs to Amazon. So its name is Amazon AWS FreeRTOS. So ThreadX name is changed to Azure RTOS, and we have the Mucos, and we have many more. So these are very famous RTOSs, and with a very small footprint. So we can run this RTOS inside the microcontroller. And third one is the embedded Linux. So if you see the block here, so we have in the embedded system we have multiple peripheral. I mean multiple domains. So it mostly in audio devices. So like the audio devices which used inside in the infotainment system of the car. So we have many gaming consoles in all the medical devices, in all the uh, on the other part of the vehicle, apart from the infotainment systems, like powertrain, chassis, body, monitoring, in telecom industries, and in industrial and home automation, which is sensor based things. So everywhere we have the embedded systems. So what is an embedded Linux? Because our focus is mostly to discuss about the embedded Linux. So embedded Linux is a customized version of the general purpose Linux. So here we have customized our Linux kernel to make it to run on the embedded targets. So today we have many architectures like ARM processor, ARM 64-bit architecture, uh, PowerPC, RISC-V, Motorola 68, and we have many more different type of architectures. So since Linux is an open source, even its kernel is an open source, so it has been customized for the different targets. And it's a shell. So shell is also modified for different targets. So basically, when we started porting this over the different targets, so those targets earlier days don't have enough processing power. Definitely, it has more processing power than controllers, but it don't have enough processing power like a PC, so that it can handle a graphical user interface like a PC. So the graphical user interface, basically, which we call as shell. So shell is a part of the core, which basically helps which helps the user to interact with the operating system. So basically, the core of any operating system is the kernel, which is directly interacting with the hardware. Those are known as drivers. It is having a hardware abstraction layer. On the top of it's having many libraries, which is also known as middleware. So middleware is consists of libraries as well as file management systems, device management systems. So when user has to interact with the system, so basically every operating system provides some kind of shell. So in embedded Linux, it has been customized as per the requirement. So if even in today's world, there are many processors which is having enough processing power which can handle a GUI like our PC, but there we have still modified the graphical user interface using multiple third-party service providers like Qt. So you can find in many embedded devices where we need a very much efficient, user-friendly, customizable graphical user interface. So that has been uh, developed using the Qts, or we have another one called Crank. So so it is highly customizable. If not required, we can just remove those layer as well, and we can have just a basic shell layer. Uh, so we can just interact using the command line interface, and most of the embedded Linux are like that. So we have different tools. So there is a confusion between the tools and the embedded Linux. So many people call Yocto Linux. So Yocto is, so I'm going to talk about these tools. So these are different tools which we use basically to create the different flavors, different types, or we have to customize the embedded Linux. So basically, we customize the Linux as per our requirement, as per our target. So suppose we are using the NXP core, or one of the most famous processor from NXP is IMX series. Basically, it was developed by Freescale, which was acquired by NXP further, and now it's part of NXP. So so basically, if we have to customize, so we use Yocto. It's one of the most famous tool which we used for creating the embedded Linux. So then apart from Yocto, we have Buildroot, OpenWRT, and Petalinux. So Petalinux is a form of Yocto, which is uh, which is mostly used, which is developed by Xilinx for their processor. So this is only meant for Xilinx processors. Apart from in among all these three, Yocto is very widely used for all the embedded processors. Buildroot is used in all those places where basically we have a very limited build in our environment. Build root also provides the flexibility for modifying the kernel as well as the root file system. But in terms of flexibility, Yocto is highly configurable. But there is one disadvantage from the Yocto is it needs a lot of space on your host machine, on your build server, because it keeps on downloading every component which is required to build the Linux. And we know our embedded Linux, though it is definitely it is a very much custom form of the desktop Linux, but still it needs a lot of packages to build a basic embedded Linux. And OpenWRT, basically, it is one form of uh, embedded Linux, which is mostly used in the routing industries. So if you go and look into all of your routers which you have in your home, so every router is basically is having OpenWRT. And in my present job, I deal with OpenWRT. So this is the file system and the utilities which is meant inside is for the networking, for the securities, it's having very easily configurable for any kind of third-party VPNs or any kind of network security stuffs, like any sort of SSLs like Open SSL, Wolf SSL, or any type of SSL you can integrate inside this. So so far, anyone is having any question? Anything from the embedded system? Okay, so I'll go ahead. So the question is why we have to go with embedded Linux. So before embedded Linux, also we used to have the embedded systems, and still today we do have. Even in the processors, we can run free RTOS based. Free RTOS based environment or any RTOS based environment. We can just run there, and we can manage our tasks based from any of these RTOS. Even we do have Unix like RTOS, like QNX, but why we go with embedded Linux? So the reason, first thing is, it's very much robust and it's having very much proven features since it was used from a very long time in the servers. So if we go and look into the history, so so it has been deployed in many of the servers, and since it was an open source, it's an open source. So for people from the different region and different companies keep on contributing a lot for its improvement. So its scheduler has been improved a lot. Lot of new features has been added, and they keep on releasing uh, new versions of the kernel. So you will be seeing now we have kernel version 6. So we never thought like a decade back we just switched back from 2.4 to 2.6, and no one thought at the time that after a decade, uh, when we have switched from 2.4 to 2.6, after a decade we will be seeing a kernel version 6. So the reason is we keep on adding a lot of security patches. We keep on adding a lot of different hardware support. Even we are improving the existing support. For example, so we had the support of PCI earlier. So now uh, we have the support for an NVMe. So NVMe is a technology which is based on PCI, but this any NVMe deals only with the SSDs. So this part has been separated out in the Linux kernel from the PCI source to improve the storage functionalities. So, inside the kernel version itself, we keep on customizing it. We are making it more specific to the hardware. So that's why there is a again challenge for those who is maintaining their previous drivers. If they have to update the Linux kernel, they have to keep on updating those drivers as well, and they have to keep on updating their knowledge in Linux kernel. Apart from that, we have a good scalability. So the scalability means we can customize it to boot from any type of storage devices. Like we can customize the Linux kernel in such a way that it can boot from a NOR flash. So those who have done Linux programming, then they know it's booting from NAND flash, eMMC, SD card, or any external devices is very much common. But when we think of booting from a NOR flash, because NOR flash is always it's a very small in size, so we can customize a Linux kernel in such a way that it can fit inside the NOR flash. So we can understand from this point like how much highly configurable it is. And apart from this, it is having a multi-platform support. So it has been ported for most of the major architectures like ARM 64, Motorola 68, MIPS. So MIPS are those processors which is used mostly in the networking domain. So PowerPC, RISC-V, and many more. Apart from this, it is very much royalty free. So like I told you, the QNX. The QNX is it's a Linux-like operating system. It's also having a POSIX layer on the top of it. So all the application which has been developed for Linux can be used in POSIX as well with a standard libc support. But QNX is not free. We have to pay a huge royalty for that. And if we keep on adding into multiple devices, so we have to keep on paying for those per devices we have to pay. So that is again where the embedded Linux is having the advantage. So now there is a question. So what if we need a real-time support? So Linux today is having real-time patches as well, which is basically a soft real-time, because the real-time patches cannot make the Linux to go into the hard real-time mode. So what if someone needs to basically have a hard real-time system using the Linux? So we do have a provision for that as well, but we need a third-party patches, third-party, we can say something like nano kernel, which is called as Xenomai or RT framework. So Xenomai has been derived from the RT framework. So it is something which when we add that in Linux, so Linux will also become a hard real time, because the control is completely taken by the Xenomai kernel, which is a nano kernel, which is very thin, and it keeps on scheduling Linux as one of its process. And the third one is easy to customizable. So it is very since it's an open source, so we can customize any of its layer, including the kernel. So we can add or delete its some of its features or majority of its features. That's what the most of the mobile manufacturers are doing. So if you see any Android, so Android is basically running the Linux kernel in its core. Only it's having a different shell on the top. So today we have like Samsung, then OnePlus. So most of them, they have customized the Linux kernel for their own architecture. Okay, and apart from this, so if today we have to develop some certain applications. So we have a lot of libraries available. We can easily download many third-party libraries. For example, if someone is coding in C++, so they wanted to make use of the Boost library, so they can just download port immediately because we have tool chains, so we can cross-compile and place those libraries inside, and we can develop the application based on the requirement. Because if you know about the Boost library, so it supports lots and lots of features. So many typical calculations, a lot of arithmetic things, and many more things. So similarly, like uh, someone is using a JSON-based um, libraries, or dealing with the JSON data or XML data or JSON to XML conversions. So we do have a lot of libraries. So development time reduces a lot using the embedded Linux. Apart from that, a general talk about this is like, now today, the um the cost of processor, which is going down, and now it is equivalent to the cost of microcontroller. So earlier, when we design a product, so at the time we have to uh, think of three aspects: the cost, the speed, and the power. So in today's world, there are many microprocessors available whose cost is actually lesser than microcontrollers. There are many microcontrollers if you look into that. So its processing power is very good, like up to 1 gigahertz, and the cost is damn less, and power consumption is also very less. So because it is completely configurable, so we can configure with a lower clock speed to consume less power. So instead of going to the microcontroller, most of the companies started moving with the microprocessor, along with the support of embedded Linux, because it reduces the cost of the development, because it reduces the time of the development. So earlier, because when if you develop the same application on the top of a microcontroller, so it will take you 6 months, and the same job can be done in 2 months using the embedded Linux, because most of the libraries are available. For example, recently we have seen the same with the 4G support. We were developing uh, one application using the 4G, and when we just look into the Linux kernel, so it has to be required with some sort of support just to enable those 4G. And once you plug in your device and you just configure your driver, the 4G dongle or any 4G devices what you are using, it can be used immediately just after configuring the kernel. Or but if the same has to be done in microcontroller, then most of the libraries has to be developed from the scratch. So going to the next point. So we have something called the MuSi Linux. So this is again a very much customized version of a customized version of embedded Linux, which is suits for microcontroller. So since the embedded Linux is getting the popularity in the industries, it's having a lot of support, a lot of libraries available. Our development time is quick. So even on the microcontroller side, companies wanted to develop the application based on Linux. So the Linux has been customized. So first it has been given a try. Can it be? So when it was tried, it worked very well. So it has been customized with the Linux kernel version 2.0. So that was the kernel version 2.0 was the first where we have tried basically to customize the embedded Linux for microcontroller. some features of the MUSI Linux is it doesn't support the virtual memory. So virtual memory is a concept where basically the operating system is uh, is fooling the microprocessor. So microprocessor understand that it is having the enough memory. So we show it like what is the addressing capability of a microprocessor. So we show it that we show the system that it is having the uh, complete memory, but it is in real it is not, and that is how the system used to work earlier, and that is also a reason that slowly our systems are getting faster because we are getting enough memory. When I'm saying memory, it is actually the RAM, where basically the operating system is getting loaded. So I'm just going to few steps back and going to explain something about the embedded system once again. So when we have when we talk about the embedded Linux, so these OS are basically having bigger footprint and they cannot be run every time from a small ROM. So it has to be getting loaded inside the flash. So basically, we store this microprocessor, this OSS inside the secondary storage devices like eMMC, NAND, or SD card, or any USB stick, and that's getting loaded during the boot process, and it's getting executed from the RAM. So basically, what used to happen earlier when we had the lesser memory, a part of this used to be getting loaded in the RAM, and the major part of this used to be getting stored in the secondary storage devices in a special section called swap partition. So processor used to execute the data which is there in the RAM, and when it is trying to access some of the data which is not there in the RAM, so that is called on-demand paging. So basically, it uh, it is getting handled by exception handlers because that data is exactly not there in the RAM. So the exception handlers are getting called, and then we swap the data because now we know in the exception handling that we don't have enough data here, but this is not known by processor. Processor is just trying to execute the next data which is not there in the RAM. So the data is getting swapped out. So from the swap partition, the next required data is getting loaded again in the RAM. So this keeps on going. So basically, might be some of you have worked on the older systems, you might be seeing it was slower than the present day system. So in present day system, what happens? We keep on increasing our RAM, and and today our RAM is so huge. Like today, I've seen people are using 32 GB or 64 GB of the RAM. So basically, it can handle almost all part of your operating system. And today, we don't need any swap partition. We can run without swap partition. Okay, coming back to the microcontroller Linux. So it is mostly used. Okay, so this is, we can say this is a cons, but by seeing the footprint, we can say it don't support any virtual memory. It is mostly used for the microcontroller application. It's an open source, so even we can customize up to the kernel level. It's having almost all the features of the Linux, all the libraries easily can be ported there. Um, yes, when we have tested this on the same hardware where we can run the Linux, so it is definitely is having the better performance than the normal Linux. And the reason is it basically don't waste its time on the MMUs. So the microcontroller Linux is without MMUs, the memory management units, which is basically meant for the virtual memory handling. Because whatever the memory we see, so suppose you write a small piece of code and you have some variable, And if you try to print the address of that variable, so that address is actually lies in the virtual memory, not on the physical memory. So again, when we talk about the Linux, so Linux got divided into two different layers. So the lower one is called the kernel layer, and the top one is called the application layer, or we can say it's a user layer or user space. So mostly we use the term user space and the kernel space. So in user space, or all of our application resides. In kernel space, we have the drivers, we have the middlewares, and we have the core kernel, which is basically driving the operating system. So uh, when we have when we basically talk about the virtual memory, so virtual memory term is separate for Linux kernel. So in Linux kernel itself, we have um, physical as well as the virtual memory, and in Linux application side, in the user space also uh, we have the physical and the virtual memory. Okay, so since it's not having the MMUs, so it's having definitely having a better performance than the normal Linux on the same hardware. So again, since there is no MMU working, there is no virtual memory, so there is no support of on-demand paging. Again, no memory protection. So why MMU has been introduced? Again, it it is providing the memory protection. So there is always a address translation, which is not happening here, because it's all based on flat memory model, like how you write a bare metal code. So there, basically, if you define a variable, and if you try to print the address of that variable, so that you will find it will be within the physical address of that microcontroller. So so here also, if you have the variable, it will be acting in the same way. If you try to print the address of that variable, you'll be seeing that address is within the actual physical space available for the particular microprocessor or controller. Also, you don't have any memory fragmentation between two different processes. So in Linux, basically, we have the memory fragmentation between the two different processes. So these are called as program address space. So every process when we launch, it's having its own process address space. So that is basically each process is having its own data section. It's having own BSS segment. It's having its own um, test segment, RO data segment, stack, and heap. So everything is separate for each process in in Linux. So basically, that is how the memory regions are protected, and most of the process, they have their own process address space, and they don't corrupt other process data. And if two different process basically in the Linux has to communicate with each other, so we have to use something called the inter-process communication, if you wanted to process within the Linux to communicate with each other. So here, that memory fragmentation is not there. So we have a mixed feeling about the microcontroller Linux. So the only advantage we see here is we have all the features, like all sort of libraries are available for the microcontroller platform. So development time is a bit easier, maybe faster. So let's discuss about the core elements of the embedded Linux. So we have totally 4 different elements of embedded Linux. So that's the toolchain, bootloader, kernel, and the root file system. So the toolchain, basically, it is consists of preprocessor, compiler, assembler, and the linker. So when we know that whenever we compile any program, so it has to go with the 4 different stages. That's the pre-processing. So preprocessor is performing pre-processing. So compiler is performing compilation. Then uh, the Okay, I will go back again and explain. The preprocessor actually generates the pre-processed file, where basically, if we talk about C or C++, so all of our preprocessors, like anything like file inclusions, hash defines, macros, everything is getting resolved there. And we get a pre-processed file where all the include files and the macros has been resolved. So most of the time the extension is saved as like .i file. So if you have main.c, so it will generate main.i file. So after pre-processing, we perform the compilation on the pre-processed file. So that basically, so whenever we use the word that we are compiling, so basically that's not so true. We have to use the word called build. So the um, complete generation of the file from source to the executable, it's called build, not just the compilation. So compilation is a part of that process. Yeah, definitely it's a major step. That's why we use the word compilation. But compilation is a part of the build. So in compilation, what happens, like the pre-processed file is getting translated into a assembly file. So now our C file got converted into assembly file. And this assembly file is based on the architecture for which we are compiling. So if it is a ARM architecture, so you will, when you see the assembly file, you will be seeing all the instruction set from the ARM. If you have MIPS processor, you will be seeing all the instruction set from the MIPS. And if you are performing a native compilation, so you'll be seeing all the instructions set from the x86 architecture, maybe from the latest processor, because there is a lot of changes in the x86. Then we see the assembler comes into the picture. Assembler acts on the assembly file, and it generates the relocatable binary files called as uh, the object files. So mostly like first time we had the main.c file, which after pre-processing got converted into main.i, and then compiler acted on main.i file and generated main.s. So that's the assembly file. Then assembler got acted on. Assembler assembled that the main.s file, and it generated main.o, the object file. So this basically contains all the binary, but still it is because all this till now, whatever the steps we have seen of the build, it has been acted only on individual files. Still, we have not yet linked these files. So now it's a time for linking these files, because we know that we keep on using different variables from multiple files. Okay, so those are not yet resolved. Apart from that, we have used many libraries. So those libraries also not yet resolved. So for example, when you use the printf, the printf basically is defined somewhere else. So where it is defined? In libc. So libc also has to be getting attached with our application. So now it's time for linking all those, resolving all those library function which we have used. So the linker comes into the picture, and it basically combines all those generated object files as well as the libraries which we have invoked, and it generates the final application. And this application is now having uh, uh, complete binary which is ready to run on a specific target. So apart from the main application, if you see the deassembly of this application, you will see a lot of other codes, like init code, like start code. These are all basically uh, inside the binary. So where it come from and what its usage. So these are certain codes which is required before your main function execute, because whatever you develop, the application inside the embedded target. So basically, you see your code starts from the main, but before main, we have certain other codes which is running. So that's init function and followed by start function. So what's the role of this? So we know because we have compiled the code for a specific target, and it is basically going to run in a platform inside the Linux. So uh, basically, these are the code which request the resources from the operating system. And when we say operating system, mostly it is scheduler here. So those are the code basically which already got added by this tool chain. So basically, when you compile the same code, same C code in Windows environment and the same code for the Linux environment, you will be seeing these things got added in both the binaries, but there is a differences. So Windows will not have the same init and start function as like same which you found in the Linux application. So that's why whatever the code for the same architecture, if you compile the code for Linux, it will not run on Windows, and when you compile the code in Windows, it will not run on Linux. So that's why this C and C++ code is very much platform specific. Platform is not just the target specific, but the operating system specific, and that's why they are much more faster than your Java or .NET code. So basically, when we talk about the Java or .NET, so Java and .NET is having their own runtime. So all this start and init function basically is there in the runtime, and that has been compiled actually for a specific platform and a specific target. So whenever you install, so you will be having your runtime already available in the in a specific target like Windows or Android or Linux. So when we generate the Java code, so basically it generates just the bytecode which interacts with those runtime, and without those runtime, we cannot run any Java code. So that's why uh, Java or .NET codes are much slower comparison to C or C++ code, because C++ code, each code basically each binary is having all the uh, runtime code within the application. Yeah, let's come back here and discuss about the other components of the embedded Linux. That's the bootloader. So bootloader is basically it's a special program which basically loads the Linux kernel. And it is there is a confusion. People think that okay, bootloader is only meant for Linux. No, it is actually meant for all the operating systems. So our Windows is also having a bootloader. Our Android also having a bootloader, and we can write our customized application which can also be loaded from the bootloader. So bootloader is an initial program. So there is a long history of the bootloader because at the beginning the kernel was not so small that it can be fitted inside any primary memory, because whenever system gets into the reset mode, it basically gets into the reset vector, and reset vector always points to the primary memory. So in the mostly what happens, like most of the time, it's some NOR flash or some ROM which is mapped to the reset vector. So we need some boot code at that level which can point or which can help us to load the secondary or the main operating system from the secondary storage devices. So that is why bootloader has been developed. So earlier days, it was developed just to load the the kernel, the OS kernel. Maybe it's a Linux or it's a Windows. So OS kernel from the secondary storage to the RAM, and from the RAM, the operating system is getting executed. So we'll discuss about the bootloader maybe on our next slides. So next is the kernel. So kernel is also known as the heart of the operating system because it is meant for managing the system. Because when we talk about the scheduler, so scheduler is a part of the kernel. We have the hardware abstraction layer. So hardware abstraction layer is also a part of the kernel. For and we have the drivers. So drivers is also a part of kernel. So it's and again, it's not just that much. We have many more things like file systems. We have multiple file systems. When you insert a USB pen drive which is having a FAT32 file system, so that is getting detected by your system because it is having a support of FAT32 file system. You can if any of you are interested, you can just try extfat. So extfat uh, extfat support was not there in the Linux kernel until 4.8. I'm not sure about the new version of the kernel, but it was not there till 4.8. So if you have any older machine and if you try inserting uh, any pen drive which is formatted in Windows using the extfat, which is also known as FAT64, so it will not be getting detected because that support is not there in the Linux kernel, so it will not be getting detected. But and if any storage device which is having a FAT file system, FAT32, FAT16, or FAT12, or NTFS, or any of the Linux file system like ext3, ext4, or ishquas fs, so any of these will be getting detected. Even it supports many more different type of uh, file systems. So file system is basically again a middleware, which basically just instruct the driver that where the data has to be written, because it is just to make the uh, data in a very much readable manner. We store those in the form of file, but file is just basically the file is an arrangement of the data in the form of linked list, and the linked list chain is also stored somewhere in the secondary storage only. That's why uh, none of the secondary storage device, suppose you get a 1 TB hard disk, you will not see that complete 1 TB of the space is usable, because most of like many of the it's a space is used for storing the chain of that linked list, because these are all uh, stored in the form of linked list. Because the idea is to, suppose you keep on adding the file, or in the future if you're going to add the file, so you can store the data in fragmented forms. Okay, so if you get a time, we can discuss about this sometime later. Now we have the root file system. So root file system is basically the another partition in the target, where which basically stores all sort of binaries. So all type of utilities, binaries, and libraries which is used by the applications. So you're very well know about this Linux root partitions. So it starts from the roots that's called slash, and we have uh, uh, like the bin, where basically we have all the basic binaries, and then we have user bin, then we have etc, where all the configurations are getting stored, and in etc we have further many more things where we have all the security stuff, networking stuffs getting stored. So let's go to the next slide. So as we were discussing about the bootloader. So let's look in a little bit more about the bootloader. So the bootloader basically, as we discussed, it is some program which helps the microprocessor to load the program which is there, or the operating system which is there in the secondary storage device. Because a microprocessor or microcontroller can execute only the code which is there in the primary memory, either ROM or RAM. So when a processor is getting powered on, so it whenever it will look into the RAM, it won't find anything, because there is no Linux kernel or something is there in the RAM. So who will be loading it? So we need a special software, a customized software. So that is called the bootloader. So it can be configurable to load a specific kernel from based on its configuration. So today, if you look into the embedded board, so we have many configuration settings there. So basically that keeps on, when you change those settings using the dip switches. So it sometimes it loads from flash, I mean eMMC, or it loads from NAND flash, or it loads from SD card, or it can load from USB based on the configuration settings. So this kind of code is basically written inside the bootloader. So basically bootloader first reads the configuration that from where I need to boot. So it by reading the dip switch, it knows, yeah, I need to boot from the NAND flash or from USB or from eMMC. So this bootloader actually earlier used to be stored in the non-volatile memory, and that time we have to make it to be basically that non-volatile memory is mostly NOR flash, which may make it to use to be getting because NOR flash memories are byte addressable, and we can directly map it to the address space. So address space, like whenever processor wanted to access any address, so it uses its uh, address lines to point a particular address. So it was very easy to map a NOR flash there. So we used to do that earlier, but it has, over a period of time, this things has been changed. Now this configuration is not there in any NOR flash, but inside the boot ROM. So the boot ROM is a part of our processor, which is resides inside the processor. So the OEM, the manufacturer of the processor, are only telling, they are only setting the configuration. So again, today also we have the different configuration setting, but this configuration setting is from the OEM only, and the code is written in the boot flash. So the boot flash also see the configuration, and it boots accordingly from the device as per the setting. But these are completely non-changeable, and it's very much safe inside the processor. So one of the most famous bootloader, one of the uh, mostly used bootloader, and was one of the most popular bootloader is U-boot. It's also called as Universal Bootloader, U-boot. The reason for using the U-boot is basically it is also an open source and cross-platform bootloader that provides the out-of-the-box support for thousands of the embedded processors. So the reason it is getting called as it is having the out-of-the-box support means it is not just the bootloader anymore today. So many companies I have seen, they keep on using the U-boot for a lot of power on diagnostics because it's an open source like Linux. So we can customize it as per our requirement. So we can keep on adding all the other stuffs. So for example, if you see that today we have a lot of advanced SoCs, the system on chip, basically, which is having a support to be getting to configure some devices before the system boots up. For example, like if you see any of the Xilinx processor. So Xilinx processor basically comes with ARM as well as FPGA. So we wanted to configure the FPGA before our Linux system boots up. So that configuration can also be done in the U-boot. So the we have the secondary storage devices like a flash. I mean, when I'm talking about flash, it's NAND flash or eMMC or some SD card or some USB sticks. So we have the FPGA binaries loaded there, and we configure the U-boot to load the FPGA first, then boot the Linux. And if FPGA is not loaded, there is no meaning of booting the Linux. So it keeps on just waiting there. Not just that much, apart from those, we have the various utilities like UUU, which is not part of, earlier it was a part of Linux, but now it's part of U-boot as well, which helps us to flash the code in the target using the UUU utilities. So basically, no need to go and change any configuration pins to make the system processor to go into the booting mode or to use a JTAG. So we can just use the uboot commands to flash the code on the target. Apart from that, it supports a lot of commands. It is having a shell. Definitely, it's open source, so highly customizable. So we can add or remove the program as per our requirement. So if someone wants to boot from a SPI flash, they can write a code inside. So your SPI system is connected, and you keep on reading the data, loading into the RAM, and you can write your own code to boot from the SPI flash. You can boot from I2C flash as well. So these are the different features we can add. Apart from that, we have many commands. So basically, if we wanted to perform or we wanted to write a script, so that is also supported. So we can write multiple scripts to perform a specific job at the boot time. That can also be done using the uboot commands. So yes, it is having a lot of environmental variables. So which we can read and write on those environmental variables. So this helps us to change the boot configuration without changing the deep switches. So suppose I want to boot, I have multiple boot media like eMMC, like SPI, NOR. I want to have a NAND flash. So I want to change the boot configuration. So I can just change those boot configurations in the uboot, and I can just save it in the environmental variable. So no need to perform any hardware changes. So I can just remove my deep switches from the hardware, and just I can make use of these boot variables. So that's all from my side. So we have like still a lot. Even if we talk for the whole day, it's less to discuss about the embedded system. So anyone of you is having any questions from anything in the embedded system?
Yeah, please go ahead. Yeah, anybody has any questions? Hope you understood the topic. Very detailed explanation brother Zafar Iqbal has taken us. Hope we understood the topic, right? Yes, no, anything? You can unmute and say something.
Yeah, Assalamu alaikum. Yeah, it was really a detailed discussion, and we have learned a lot.
That's good. Yeah.
One simple question, brother. Like, I am working on Zinc platform, Ultra Scale Plus. So, as you have also told about Xilinx has a processor and the FPGAs parallelly. So, the chipset on which I am working, it has 4 core of F53, 2 core of R5, and then PL side, FPGA side. So do you think there's a lot more different in customizing Linux on this platform than what we generally do?
Okay, so basically, you have the Peta Linux there. So they have already customized whatever they can, Xilinx. So yes, because there is no end. Because prior to this, I was working on the same platform, and the top telecom companies use the same platform, the Xilinx Ultra Scale Plus. And if you go to the Peta Linux configuration, so you can do a lot of configuration there as well, like like a booting system. So what I have seen, the company has introduced because they want it's a telecom company and they wanted to safeguard their hacking system. So basically, they keep on putting their binaries into the different locations. So different location in the sense there is something called eUSB. It's a very new term, and it's a form of USB, but it got embedded on the chip. So basically, uh, it has um, it has the init ramfs file system, which got embedded everything inside the image.ub file. So that used to place inside the NOR flash. So what happens? They used to keep all the complete. It's called a monolithic image. So the complete monolithic image they used to place inside the NOR flash, which is not at all accessible because it don't have any file system. And all their after booting, all of their files, because it's a init ramfs, so all the file system is actually resides in the RAM. But many of its folder where they wanted to lock the non-volatile data used to be getting mounted in the um, eUSB. And eUSB is something like a chip which is basically mounted on the board, but there is a provision to take them out and can plug in any USB devices. So this was very much customized from their side. So again, in the older version of the product, as you told, there are 2 cores of R5 running on that. So I have seen they have used ARM Cortex M4, which it was a part of Xilinx Zinc 7. Okay, so Zinc 7000. So they used to run actually FreeRTOS on ARM Cortex M4s and Linux on all the other cores. So a lot of stuffs were done by M4 and a lot of stuffs done by the ARM. And basically they used to exchange data. So those cores were able to access the RAM, and Linux, you cannot access the RAM directly. You have to write a driver code where basically you to perform IO remap. Then after performing the IO remap, your pointer will be started pointing to a uh, particular location. Basically, it is also a translation. So these kind of stuffs they have done. So other part of customization is, which was a unique customization I've seen in the Ultra Scale Plus, which is having a 4 symmetric cores A53. So they used to run FreeRTOS in 2 cores and FreeRTOS on Linux on 2 cores. That was a wonderful porting. So so such kind of customization I have seen. So it's all like based on application, they keep on customizing. Prior to this, I have seen not in Xilinx but in Altera. That's a platform called Cyclone 5. So that's also having a FPGA along with ARM cores in the single chip. So there I've seen the company needed multiple processor because 2 core was not enough. So they have converted the FPGA also into the cores. So there basically they started. So they were soft cores, so 2 hard cores, 2 soft cores, and in the soft cores they started running RTOS. In the main hard cores, Linux was running, and they used to exchange the data. A lot of challenges, a lot of interesting facts comes from there. So did I answer your question, or you wanted to ask something else about the customization part? Because there are a lot of other things to be done. Yeah, please go ahead.
Yeah, it's a really good input. Like we are looking for something like that because we are not happy with the only Petalinux solution. It is having some performance this thing. Have like one specific question, like we are planning to move towards Wind River, like we recently heard about it.
Mhm.
Any inputs on that software
WinRiver to have a support, but
comparison
when
between Petalinux and WinRiver, if
yeah,
you
Beta
can
Linux is completely
highlight
free.
something on.
Yeah, Beta Linux is completely free because they are meant, because Xilinx is selling their product. So what happens, like when you go for with Beta Linux, they will definitely provide a free support for that, because you're buying the hardware from them. But WinRiver will charge you separately, and they do have a good support, but configuration is not very good as like Beta Linux, because um, I will just give you an input. I was working in Infinera. That's my last company in India, and we used to work. The actual assignment was we were moving from the Wind River to Beta Linux, version 2020.2, with a kernel version of 5.15. Earlier, 2018, we had 2018 to 2018 is having kernel version 4.1, 4.8. So whenever you update the Beta Linux support, the version, so automatically your kernel version will be getting upgraded. So like, uh, but we keep on doing a lot of hardware stuffs. So can I ask what is the performance issue you got in Beta Linux?
Yeah, it's like we are working on 5G solutions,
Okay,
and like actually there's another client for which we are working on WindRiver, like Altera, the Cyclone platform also.
okay.
So when we have seen the performance of on Cyclone with the WindRiver, it is better than the Petalinux.
Yeah, that depends on completely customization. So basically, it depends on how you are customizing. So as I told you, like there is a very good documentation about the Beta Linux. So if you go and see, you can that is the best tool I have ever seen, and I wish I could have got that for all the other tools, because the Beta Linux provides you the different commands for customizing the different components. For example, if you wanted to customize your root file system, so you can just okay. So can I ask you what is the root file system you are using? Uh,
You're not pretty sure, like so like we generally go with the default one.
yeah, okay. So basically, there are different type of root file system supported. So I have seen most of the companies go uh, uh, with init RAMFS. The reason is the whole file system resides in the RAM, and it's a damn fast. It's very fast. So we have the option to customize the root file system. We have the customize to we have the option to customize the Linux kernel. We have the option to customize the U-boot. So a lot of things are there. So like what we have seen is like we have moved from 2018 to 2020. So that was one porting we have done, complete platform work. A lot of challenges because kernel version itself has got changed. So a lot of changes need to be done in U-boot. And we moved from this Monta Vista Linux to Peta Linux again 2020.2. And that was also a big challenge because lots and lots of file system, the configuration, everything needs to be changed. So I had a different opinion, but yeah, because if you have some code already given by client and they are working on Monta Vista Linux, so basically you have to go with that, because uh, you cannot stick with Peta Linux at the time.
No, these are two different projects actually. So the
Okay.
like the client one is different, and we have our own product development. So
Mhm.
for this, we have the right to choose. So we are still in dilemma, like to which platform we should stick with.
Okay. So which version of Peta Linux you're using?
By now, we were trying with the 19.2, but recently we have so evaluating 21.1.
Okay. Yeah. So I think the latest version may have the good features. So because at the end of the
Okay,
day, it's all the open source, right? So basically it depends on how deeply we
true.
are customizing it. right? So if you customize, you can keep on trying the different file system and can see the performance, like the initramfs, the ext4. So yeah, if there is some issues with the booting time, definitely when you have initramfs, it will be having a higher boot time because it has to mount a lot of file system in the RAM, initializing the RAM, mounting the file system there. But at the end of the applications will be faster enough. So uh, yeah, that's my feeling actually.
But whatever deep customize we do, still it's non-deterministic, right? For RT, like for real-time applications, is it still suitable? 5G, I'm
Okay.
talking about like 5G solution to be more
Okay,
specific.
okay. So I will tell you, like the reason when you talk about even every telecom industry, they use Xilinx. Most of the 99% of the companies use Xilinx. Okay, the reason is, see, the what the role Linux is playing here is not the real time. The real time job is playing by FPGA. Okay, so and that is why the Linux is just acting between. It is performing all the non-critical and configurable configuration stuffs actually. Okay, all the data packetization, definitely even our a very hard real-time microcontroller will not be suitable for that. So that can only be done by the FPGAs, and our Xilinx FPGAs are very well powered, so it can handle all those stuffs. So definitely 5G, because I will tell you, we were dealing with data transmission in the form of uh, laser. So the data what we have tested with the same processor, Ultra Scale Plus, it's 1.6 terabytes per second in the form of light lasers. That is how I told you, like the company name is Infinera. So they basically deliver. They have their IE6 optical engines. So basically their products now they have tested with 1.6 terabytes per second. So that is how the data is getting transmitted over the optical fibers. And that's how today you and me are communicating. So I'm sitting in one corner of the world and you are sitting there, but there is no lag. So we are able to communicate very fastly. I think. Look, so these are all happening through these processors only.
Okay.
Yeah.
Thank you very much. Like,
So yeah, welcome. So anyone else is having any question?
Okay, if no more questions, I think we can wrap up here.
Yeah, so I just want to point one thing about if students are there in the call. So just wanted so I wanted to add some motivation lines because the reason, as I told you at the beginning, the main reason to choose this topic today is because I'm seeing a lot of demand which is increasing for the embedded Linux. So basically, if someone wants to start it, so basically there are a lot of courses available in Udemy as well. So basically, we can start from there, and mainly focus should be like from where to start. So I'll suggest start with the application development and slowly go inside the system boot up process and kernel. So look into the hardware, basically how it boots up, from where it fetches. So uh, like I have seen the requirement keeps on growing globally, not just in India. It keeps on growing across the world. People are looking a lot for the embedded Linux developers. And today, at present moment, there is a very much lack of embedded engineers, especially in Linux side, because from a decade people stopped coming in the embedded system side. Most of the students, they keep on moving towards the AI or machine learning side. So if if there is no platform, then where the people will develop these applications. So so only these are the notes which I just wanted to add, because definitely it is a very much interesting field. Like if someone is interested, they can keep on developing. They can customize a lot in the U-boot and Linux, They can create their own version of Linux kernel. They can make the system to boot from anything what you want. So basically, you can become a system programmer. You can basically make the system the way you want to boot. You make your system to get control the way you want to control. So yeah, that's all from my side.
Good. So one question here.
Hmm.
So how do you relate this embedded Linux in the IoT space? Like what are the opportunities you are going to have there?
Okay, again, when we talk about IoT, so basically, uh, when you see IoT means we are connecting each and everything. That is the target, to connect each and everything with the internet. So definitely you need uh, a lot of sensors, and you how to control or monitor those sensors using some microcontrollers, because we have to look at the cost as well, cost, power, everything. But how these small microcontrollers will be communicating with the internet? Definitely, they need some sort of gateway. So most of the gateways, if you see, those are Linux based. So and the usage and there is an advantage, because when we talk about IoT, so there is the major concern for the IoT is security level. This IoT, actually, we are hearing this term from past 8 years. 8 years back, we have heard first time about the IoT in 2014. At a time, basically this word was coined long back, but it got popularity in 2014. But till today, you won't see like we have enough IoT devices. Still, it is in very much prototyping phase, or still it is used in very specific places. The reason it's people are much more worried about the security. So the issue with the security is, like if someone, suppose suppose you have the access control of your home from using the IoT, and if some hacker hacks it, so they can open the door and they can steal the things from your home. Similarly, they can do a lot in your vehicle or any connected devices. Someone someone simply, if your bulb is connected to IoT, someone just for fun, they can start switching on, switching off, all these things. Okay, so security is a major concern. So these securities can be provided using the gateways, because this security feature, because we have a good uh, good security libraries, like we have Wolf SSL, that embed SSL. So apart from that, we have Linux firewalls, which is very much difficult to break. So the intruders cannot enter. So the first thing is like gateway. So the gateway is the entry point for any IoT command inside any industry or home. So and this gateway can interact with multiple edge devices, like sensor which is connected to a door, or anything, any devices like your washing machine, refrigerator, or a rice cooker. So all this data can be monitored or controlled from the remote, and all the entry is via the gateway. So most of the time, the company choose to have a embedded Linux device there instead of just a plain microcontroller. We do have the capability. We can use. We can definitely develop a gateway using a ESP32, and we have done that, because ESP32 is having enough processing power that it can be act as a gateway, and a very cheap gateway, because it's the cost is very cheap, actually, because you can just get for 500 rupees, you can get an ESP32, or max 1,000 rupees. um, and it's having dual core, 240 megahertz each, and you can control and you can make this to act as a coordinator for Zigbee. So all the other Zigbees will be connected to ESP32. Apart from that, you can make the Bluetooth, because it's having a Bluetooth supportability as well. It's having Wi-Fi, so basically everything is there. So using the Wi-Fi, it can connect it to your router, and on the other side, using the BLE and Zigbee or other protocols, it can be connected to multiple edge nodes in your home. But security is a concern here. So definitely, by seeing today's cost of other processors, which is running embedded Linux in it, so definitely Linux-based device is preferred.
Okay, thank you. Any other questions?
Yes, sir. Sir, I have a small doubt regarding to a gateway.
Mhm.
What is the main function of gateway in the IoT devices? Like just recently you said like in the security level of IoT is a
Mhm.
necessity, and you
Yeah.
gave also example. The actually I was working on the last company which is based on the like hardware and software also both, but my work is very small. So the gateway is the main function, but we can't get the understand the life's last company in the gateway. What is the gateway purpose on the IoT level?
Okay.
So if in the
As
sir,
the sure, sure. So as a name suggests, the gateway is something which is the entry point. So this is a gateway for the IoT traffic to come in or to go out. So gateway is something like close to like your router. So in your home you have a router, and it is connected to multiple devices, your laptop, your mobile phones, your desktops. Okay, sometime with printer as well. So the gateway do the similar job. It is connected to all the edge nodes. So edge nodes are the edge computing devices, like your door. So there is a sensor in the door, and it is controlled via um, uh, microcontroller. So the microcontroller definitely it will be having a communication media like a BLE or a Zigbee. So the status of door is it's closed or open. It will get via the sensor. So whom it will be communicating, it will communicate to the gateway. See, on the same side, suppose it is a Zigbee. So in Zigbee, we have something called coordinator and end nodes. So the coordinator is basically which forms the network. So the gateway will be acting as a leg. So what happens? You have to the gateway should have the capability, or it must be attached with the coordinator. So the coordinator is forming a mesh network in which all the other Zigbee devices will join. So via this coordinator, the gateway will have the control of all, can control or it can communicate with all the other edge nodes. Similarly, when if it, gateway must have, so gateway must have all the features. So it must have definitely the Zigbee, it's already having attached with the Zigbee coordinator. So it is good to choose such a processor which is having the Bluetooth capabilities, which most of the Linux based system is having today. So you can enable the Bluetooth or BLE, and you can make this to communicate with with other Bluetooth devices. So so when the traffic comes and on the other side, it should have either the Ethernet connectivity or the Wi-Fi connectivity, using which it will be connected to your router. So on the other side, it is connected to the internet using Ethernet or Wi-Fi. So one side, it is managing the traffic which is coming from your IoT. So IoT basically it's some cloud. So you can have your own customized cloud. You can have AWS or Azure or IBM or anything. Now we have plenty of clouds today. So that has to be configured. So you will be having a so today what we use mostly. So most common used IoT software is software protocol is MQTT, the message queue telematics transport. So we can develop the MQTT client, which will be residing on your gateway. So it will be managing the traffic. The MQTT will be connected to MQTT broker. So where the MQTT broker will be, it is already deployed in your AWS. You can deploy it in your own cloud. You can make this to You can connect to any third party just for testing purpose. You can connect it. So yeah, this is basically the gateway. Apart from this, these are not just the limitations. We can still extend its functionalities. For example, we can attach a CAN trans receiver, and we can connect a multiple, because CAN supports multi-drop. So over the same line, we can have multiple devices. So you can connect. So you have a wide communication also. Which side? On the other side of the gateway, where basically you are controlling the devices. For a reliable communication, you can have CAN, you can have a serial communication, you can have USB devices, you can have a RS-485, or you can still have other Ethernet-based communications on the other side. So yeah, these are the certain features of your gateway.
Yeah.
Did I answer your question?
Thank you, sir. Thank you.
Yeah, it was a very detailed response for that question. Good. So any other question? So if no more questions, I think we are good with our time as well. So I thank all the participants for taking out your time on Sunday. That shows the curiosity to upskill yourself. I think it's a great opportunity for all of us to have Brother Zafar Iqbal, who is an expert in this space. So for every question, we have seen the way he has answered to the detailed level. So it shows the expertise he has. So Jazakallah, Zafar Bhai. It was a very insightful session. I think we have covered a little of it. There is a lot to hear from you. So we would be requiring a lot of series of sessions from you.
Yes, sir, inshallah.
Yeah.
Yeah,
So,
there are a lot. Actually, as I told you, like even a whole day is less for talking about embedded side.
okay. Yeah. Thanks. I think I just shared the link here in the chat box also. So the recording is going to be there in tinyurl.com/mfrd. So all other recordings in the past, whatever we had these sessions, those things also you can see there. And if you are an expert and if you want to share something, so you can reach out to us. We can have a session from you as well. And if you know any experts in your vicinity, you can again convey that message to us so that we can have them also in this platform for the benefit of the larger audience. Thank you. Thanks a lot. Jazakallah khairan kaseera wa jaza. We'll
Thank you.
close for the day. Thank you.
Thanks.